Hi, welcome to this video about NCS 5500 route scale. Here are the topics we'll cover today. How we can learn a full internet view on base systems. How we will monitor the ASICs resources with counters and streaming telemetry. And finally, how we will handle internet growth. Let's get started. In this video, we'll show you the routing scale of the NCS 5500, and more particularly, we talk about the line card and system not using external eTCAM. For instance, we are talking about the 36 by 100 GIGI line card, the 18H18F, the coherent DWDM line card, and the MACsec line card. None of them are using external eTCAM, just the memory inside the forwarding ASIC. Same thing for the fixed form factor platform, 5501 here. Also, we have one version of the 5502, not using external eTCAM. Here, the 55A124H, and finally, one version of the 55A136H exists without external eTCAM. The demo will be fairly simple. We will have 15 times the internet advertised inside our router, and this router will be a 5508 chassis with a line card, not using external eTCAM. We are talking about real internet routes here, something recorded through real v4 and v6 internet views. So we will have 15 times the internet v4 and v6 advertised to the box and received by our BGP process. All this information is installed inside what we call the edge RIB in. This memory will be after the RPL application. This information is going into the local RIB, and finally the local RIB will populate the routing information base. This base is also populated with other protocols like OSPF, ISIS, or even the connected and the statics. That all these protocols or sources will populate the RIB. Then the RIB is passing route information to the FIB and to what we call the DPA. DPA is data plane agent. This data plane agent will use address family, v4 and v6, but also prefix length to decide where the routes should be stored inside the forwarding ASICs. For instance, we will have different bases, the LPM, the LEM, but also in some other line cards we will have the external eTCAM here. That's where the prefixes are stored, but also we'll have the next stop information stored here, and also the load balancing information, and the encapsulation database is also one that will be populated here. So it's going to be very important to leverage the different size of these databases, and to do so we will use the different prefixes and different prefix length we have to optimize the distribution. So let me show you now how we're going to do that with a real router. This is our 5508 with the line card we'll use, which is in slot 2. That's the one here. That is the 36 by 100 we will use for this test. Show BGP sum will show me how many prefixes are advertised from each neighbors. I have 15 of them advertising the full internet view, v4, but also v6. All the, so BGP indicates summary. So if I do a show BGP simply like this, for each prefix I will have information of next stop, AS path, but also local pref, metrics, etc. All the BGP attributes. I will have the same also for IPv6 unicast. This is my V6 routing table and all the path. So I'm talking about real routes here. That's a use case where the router is used in a peering role. I can also check the number of paths I have in total. With the show BGP scale, I will have number of prefix V6 and V4, total 760K, and the number of path is almost 10 million, and we can go actually much higher. And this is a memory it represents inside the routing processor. There is also ways to show this information with streaming telemetry. The router is generating streams of counters to a collector, and I can see in real time my V4 table, size, V6 table, but also the number of paths, 9.9, almost 10 million paths. So in real time I can see that, and I can see how it evolves. That's for the BGP part. Now, if I want to take a look at my RIB, I will just simply do a show route. And here I will see that some routes have been learned through BGP, some others have been learned through static, and if I do the same thing for IPv6, I will see that I have routes learned by, they are connected, they are local, and some others are BGP. So this is the different processes that have been populating my RIB table. Now this information is passing through the FIB and the DPA, and here the important information will be the prefix distribution, because we want to optimize the way we're going to sort the routes. So I type show DPA resources IP route, location 0/2, which is where my line card is, and I can see, depending on the prefix size, how many entries I have. And that's very important because that's really where we'll do the optimization. And same things exist for IPv6. I will say the most important one for IPv6 being /48 present here. So that's all the DPA is receiving, and depending on the prefix length, I will decide where it should go, LEM, LPM, etc. So I will take a look at my controllers, show controller NPU resources, LEM for example, location 02, and here I can see the maximum size. For LEM I can store up to 786K entries, and what is currently used for, let's say, 410K for roughly 52%. Okay, and for LPM now, I can see that I estimate the maximum number of entries at 430K, and I currently occupy 81% of this capability. This number, 430, is actually dynamic depending on the prefix distribution. It varies between 350 and 450, more or less, depending on the way you are sorting routes. So I do have still 19% available here. Same information is available through streaming telemetry. I can monitor in real time how many LEM entries I'm using, how many LPM entries I'm using. So that's really showing that 15 times internet can be stored in a non-eTCAM system and still use only 52% of the LEM and 91% of the LPM, knowing that most of the new prefixes will come here, /24, /23, they are storing here. How does it work exactly? By default, all the prefixes are going into the LPM aside the /32. Not very useful for internet distribution where we have a lot of /24, /23, not that many /32. So that's why we done the first improvement, which is a default mode when you run the system. We are using 32 and 24 in LEM, and the rest goes in LPM. And for IPv6, all the /48 are going in LEM, and the rest goes in LPM. That way we are leveraging the largest database, which is the LEM. But it's not enough. We did some other improvement, something we call the Internet Optimized mode, and this mode is simply changing the order of operation in LEM and LPM lookup. We don't change anything on the IPv6, all the /48 are going in LEM, but on the IPv4 side, we no longer give a lot of importance to /32, it's going into LPM. We are giving more precedence or more importance to /20, 23, and 24. All this will go inside this LEM, and that's a good thing because that's the most important route population on internet. So The question will be, how far can it go? We are using this growth projection based on the information available on these two Twitter accounts. BGP4 and 6 table are showing every week the distribution of routes depending on the prefix length. That's a good thing because we can see a trend and decide which one are growing for IPv4 and IPv6. We see that /24 is the fastest growing population, and for IPv6 /48 is the biggest one. We can see that in the future it will go like this for LEM and LPM, and we can also identify where we're going to run out of resource. LPM, we have 786 entries, K entries, that's something around here. And for LPM, we have 430K, which is something around here. So we take the earliest date, and that will be something between 2021 and 2022. So we can safely say that we can use this line card with the current growth projection between 2021 and 2022. Thanks for watching. Hello and welcome to the second video on the NCS 5500 route scale. My name is Nicolas and I'm part of the technical marketing team in Cisco's Service Provider Business Unit. Last time, we presented you how it's possible to store a full v4 and v6 Internet table in NCS 5500 systems, not using external eTCAM. And you can check the video clicking here. Today, we will present you a situation where you need even larger routing tables, and that's the purpose of the system based on Jericho forwarding ASIC with external eTCAM. It's an external memory that offers up to 2 million extra v4 entries. We will detail the logic used to sort the route between the different internal and external resources, and this with concrete, real-life examples. Let's get started. We have seen many use cases where very large routing tables are required. First, we need to support the full view, v4 and v6. You will get different answers depending on who you ask, but it's common to receive 700,000 v4 routes and 65 to 70,000 v6 prefixes from your transit providers. Second, you will have your peering routes. The routes you're going to receive from your partners will be more specific than the one present on the internet, and you can add dozens of thousands of routes to your table. Third, you have your IGP routes, ISIS and OSPF. It will depend on the size of your network, the number of routers, the links you have, the way you manage your areas. 4, it's not unusual to see a lot of host routes in the network. They are advertised by DDoS mitigation systems, or they are present because you are doing a lot of virtual machine migration. And I've seen network with multiple times hundreds of thousands of /32 routes in the table. Finally, Internet is constantly growing, and we've seen that in the former video. We expect the routers today to be able to support the size of Internet in 10 years. All these reasons justify the use of systems based on external eTCAM to accommodate today's and tomorrow's requirements. For this demo, we will use NCS 5508 chassis with 24 by 100 gig line cards. These line cards are based on Jericho ASICs with external eTCAM. The operating system is sorting the routes based on address family and prefix length. In the former video, we detailed the specifics of the internal memories. LEM is capable of 768,000 entries, and LPM is algorithmic, and the size will depend on the prefix distribution. Today, we introduce the external eTCAM, capable of 2 million v4 entries. In 623, these 2 million entries are split in 20% for access list and 80% for IPv4 routes. But this default carving can be changed with configuration. Now let's take IPv4 routes. The /32 will go in LEM and the rest will go in external eTCAM. For IPv6 prefixes, the /48 will go in LEM and the rest will go in LPM. To put things differently, in LEM, you will find your 32 IPv4 entries and you slash 48 IPv6 entries. Also, you will find MPLS and MAC address information. The LPM, you will find your IPv6 route aside the slash 48 and the multicast entries. Finally, in the external TCAM, you will find your IPv4 routes aside the slash 32 and access list entries. Let's illustrate all this with a real use case. First, take a look at the chassis. In slots 6 and 7, you will find 24 by 100 GB line cards with external TCAM. A show route summary and show route IPv6 unicast summary will give you an idea of the size of the tables v4 and v6. You have 1.2 million v4 prefixes and 63,000 v6 prefixes, mostly coming from BGP. A show DPA resource IP route and IP6 route is a very useful command to identify the way we are distributing the prefixes in terms of prefix length. Interesting to notice, we have 436,000 /32 v4 host routes. And we will repeat the same operation for IPv6. We see this time that the /48 is the largest population and we have 21,000 of them. The show controller NPU resource will display the utilization of the different databases internally and externally. We use 58% of LEM, 9% of LPM, and 48% of external TCAM. More specific to the external TCAM, you can use show controller NPU x TCAM to take a look at the carving and utilization. We can use Grafana to visualize the same information streamed by telemetry. Let's project ourselves in the future and see what will be internet size in 2025. It's certainly not a very rigorous approach. We picked the last couple of years and we identify what was the growth for each prefix length, and we derive this information to the future. So let's say it's an approximation of what internet will be in 8 years from now. We configured these projected new routes and advertise them to the same router we use in former test. Total represent 1.6 million IPv4 prefixes and 108 IPv6 routes. Now the question will be, how much does it represent in our different memories? It will be 62% of the LEM, split in IPv4 and IPv6 prefixes. It's 12% of the LPM with only IPv6 entries. And it's 72% of the external TCAM v4. So we have still quite a lot of empty space with a super large amount of host routes and the 2025 projected internet size. To conclude this video, we've seen that we have situations where we're gonna need very large routing tables today and certainly tomorrow. With the NCS 5500 portfolio, we have routers and line cards in chassis using Jericho chipset and external TCAM. This external TCAM will offer 2 million extra entries. Total 3 million routes. So we can accommodate today's and tomorrow's needs with these systems. In the next video, we'll show you how we can mix base and scale line cards inside the same chassis. Thanks for watching. Hello and welcome to the third video of the NCS 5500 route scale. In the last episodes, we described in details the two different categories of systems and line cards, the base versions, the scale versions. The main difference between the two being the presence of an additional external TCAM. It's a memory that offers some extra resources to the forwarding ASICs. For instance, routes or prefixes and access list entries. Now, what happens if you mix base and scale line cards inside the same chassis? Today, we will describe in details a feature called selective route download, and it has been designed specially to address this particular use case. The main purpose is to select the routes you want to be present in the base or scale line cards and avoid potential saturation situations. So, how does it work? The IGP routes, ISIS or SPF, but also connected and static, will be programmed in all types of line cards. We don't differentiate anything here. The BGP prefixes, by default, will be programmed also on all types of line cards. When I say by default, I mean if you don't change anything in the configuration. It's possible to mark selectively the BGP path with a flag named external reach. The route with this external reach flag will be programmed only on the scale line cards. In terms of configuration, it will go under router BGP, your AS number, address family, v4 or v6, and it will be a table policy with a policy you defined earlier. We can decide to mark all the routes coming from a BGP peer, or if we want, we can select some routes based on parameters like the prefix length. Let's take an example. I want to mark all the routes coming from a BGP peer. I want to set the external flag, and that means I want to program them only on the SC cards. For that, we'll proceed in 2 steps. First, I will mark the routes learned from this peer with a specific community, 100 column 111. Second, I will match the entries with this community in a route policy high-low fib. It will mark this route with a path color external reach, and I will call it in a table policy under my BGP address family statement. With this configuration, the BGP route advertised by this peer.151 will be only programmed in the -SE cards. Another example. Here, I want to program all the routes received in my scale line cards, but only the /32s inside the base version. I will define this route policy high-low fib, where everything with a prefix length from 0 to 31 will be assigned a path color external reach, and the rest will be accepted, but not colored. For instance, the /32s. And I will call this high-low fib in a table policy like we did in the previous example. We will illustrate this in a few seconds with a demo. In this demo, we will use an 8-slot chassis with 4 different types of line cards. In slot 2, we will have a 36 by 100 board with 6 Jericho ASICs, no eTCAM. It will be the base line card we will use for the demo. In slot 7 and 6, we're going to have 24 ports 100 gig and a 24 plus 12 respectively. Both are using Jericho ASICs with external eTCAM. They are -SE or scale line cards. Finally, in slot 1, we have a 36 by 100 SE. It's also a scale line card, but running a Jericho plus NPU with a second generation of external eTCAM. First, we inject 30,000 ISIS routes, and we verify they are programmed in all types of cards. Let's check the route count with show route summary. With show route, we see we generated only IPv4/24. Then, we check on each line card where they are stored. Slot 1, the routes are programmed in the external eTCAM. We verify that with show controller NPU resources xtcam IPv4 location 0/1/CPU0. On slot 2, which is a Jericho without external eTCAM, the routes are programmed in LEM. Slots 6 and 7, the routes are programmed in this external eTCAM. So, all ISIS routes are programmed on all types of line cards. Now, in the second part of the demo, we inject a very large BGP table. It's a full IPv4 internet view with also a very large amount of host routes. It represents more than 1.1 million entries, and among them, 434,000 are /32s. So, it's more routes than the baseline card can handle. We can create a policy to mark all the BGP routes except the /32 with a path color external reach. That way, only the IGP and the /32 will be programmed in the baseline card. Let's check the baseline card in slot 2, show controller NPU resources LEM, location 0/2, and we see 464,000, which represent the 30K ISIS routes and the 434K /32 from BGP. We can check on the other slot that the scale line cards are learning all the routes. For instance, in slot 1, we see we have 1.2 million entries. And the same in slot 7, but this time the routes are split between external TCAM and LEM. See that with show controller NPO resources, external TCAM v4, and show controller resources LEM. To verify where a route will go, just use show route. For example, a show route 1.1.107.0/24 displays external reach LC only, while some other show route on a /32 will not give the same output. So now we understand how we can manipulate the coloring of the routes to decide where they will be programmed. Before we wrap this up, it's important to cover some element of network design that could seem a bit counterintuitive at first glance. When I design a network, where should I put my base and scale line cards? In front of my core, or in front of my peering or my content servers? To answer these questions, we need to understand the way things are working inside the forwarding ASICs. The lookup of the destination is performed essentially in the ingress part of the pipeline. That means when a packet is received on the router, I need to have the routing information on how to reach the destination on the line card where I have my ingress interface. And it's significantly different from what we used to do on the more traditional platform running iOS XR. So let's take an example of a peering router, something positioned in front of internet peers. The packets received from the core router need to find their way out to the internet. That means the ingress line card should have the full view in the feed. That's why you need a scale or an SC line card here. When the packets are received from the internet to an internal host, you will only need the route to this address, or to the lookback of the router used to reach this address in case of MPLS transport. That means you can use a baseline card on the internet-facing ports. I will put some other examples in the blog post that will be published with this video. To conclude, we explained today how the NCS 5500 can be configured to select precisely the prefixes you want to program on one type of line card or not another. This mechanism, called selective route download, can be used when you need to mix base and scale line cards inside the same chassis. Don't hesitate to ask any question in the comment section of the video or the blog post. We'll be very happy to hear from you. We hope this was informative. Thanks a lot for watching. Today, let's talk about security on the NCS 5500, and more precisely, let's talk about what we call hybrid access lists. My name is Nicolas Février, and I'm a technical leader in Cisco's Service Provider Business Unit. In a recent article on xrdocs.io, we presented how traditional or flat security access lists were implemented on the NCS 5500 routers. We invite you to check this article if you are curious to understand how a flat ACL works, where it can be used, where we store the data, what is the scale, and many configuration options. You can find the link in the description of this video. Today, we will demonstrate the flexibility and the really impressive scalability you can get with another kind of access lists, the hybrid ones. It's a feature sometimes named scaled access list or compressed access list. It's the same thing. First thing to note, we need a specific hardware architecture to operate it. That's why it's supported on routers and LAN cards based on external TCAM only. They are easily identified by a -SC at the end of the product name. Hybrid access list requires external TCAM, and it's true whether the product is based on Jericho or Jericho plus ASICs. Second thing to note, hybrid access list can only be applied in ingress direction and can only be used for IPv4 and IPv6. We'll start introducing the concept of object groups. For instance, network object group and port object groups. As the name implies, it's a simple construct made of prefixes or hosts on the one hand and list of ports on the other hand. For example, this network object group for my email server contains 17 entries, host routes, but also networks like /23, 24, 25s. But these port object groups contain the ports I want to open for my email servers, and they have 8 entries in it. In a traditional or flat access list, I will need to create one line for each host and prefix, and for each one of them, I will need to specify the port I want to open. In my case, that will be 17 by 8, that's 136 lines. With hybrid access list, that can be reduced to just one line. Permit TCP/NE, net group, object email nets, port group, object email ports. With this single line, I'm describing traffic coming from everywhere and every port, and targeted to the matrix composed by every combination of the element of my net group and port group. With the expanded keyword in this show command, I can verify that indeed it's 136 entries. Of course, my access list filtering can contain hundreds of permit and deny lines, and they can be based or not on net group and port group. Now, let's imagine that I have a new email server in my network. I simply need to edit my object group and add this .157 host address. Automatically, all the relevant ports are added to it. And the total of entries moves to 144. You understand easily now the flexibility this approach brings in your access list management. But I also mentioned scalability. And indeed, with hybrid access list, we can create huge filters, things that wouldn't be even remotely possible with a flat access list. On one line of access list entry, we can use object for source and destination, addresses, and ports. So it's potentially a 4-dimension matrix. Let's take a very big example to illustrate that. I will use a source of net group of 500 entries with a port group of 500 entries also, and a destination net group of 50 entries with a port group of 10 entries. That single line represents 125 million lines of a flat access list. What does it represent in terms of memory occupation? A part of the access list will be placed in the internal eTCAM, for instance the destination ports, and the rest, the source and destination prefixes and the source ports, will be stored in the external eTCAM. You can see the numbers in this show comment. Something also very important to mention, the performance in terms of packets per second is not impacted by the application of this access list. I invite you to read the blog post for more technical details, like the compression or the carving of the external eTCAM, and actually much more. I hope this was useful. Don't hesitate to ask questions or provide your comments. We are looking for your feedback. Thanks a lot for watching. See you soon.